Welcome back. This is part 3 of lecture 5, and we're going to talk about complete subset regression. Okay? So the references are these two papers by Elliott, Gargano, and Timmerman. All again, both are available on our Google Drive folder. Okay. So the idea is the following: a method for controlling estimation error in forecasting problems that involve small sizes and many potential predictors are popular, like Lasso, for instance. Okay. And basically what we know is that including all possible variables is typically not the right thing to do. So it's important to limit the number of parameters. So we can do some sort of shrinkage with sparsity inducing methods like Lasso and friends, or non-sparsity inducing like Ridge, for instance. Or we can do bagging, or we can do boosting. Here I'm going to give you a different alternative, okay, that have some very interesting results in practice, that in some cases, if you are interested in pure forecasting, pure prediction problem, no inference, but if you're interested in predictions, there are some nice empirical evidence that this method works nicely. Okay, so the idea is to combine forecasts, and how we are going to do that. Basically, we are going to estimate models using subsets of the variables. Okay, and the idea is how to construct these subsets. So take, for instance, a situation where we have k possible predictors, okay? And imagine that we are going to estimate, we have like k unit variate models, okay? Because we can run each predictor a time, but we can form like all the possible regressions with 2 predictors, all possible regressions with 3 predictors, with 4, 5, so on and so forth. So we have, when we have like capital K predictors and we are looking at lowercase k variate models, that this is the number of models that we have, like factorial of k divided by the factorial of capital K minus small k factorial, okay? And this can be large, right? So take some examples with k like equal to 20, 30, or even 100 or 500 as we have in some applications, or even more. And if you look at all possible combinations, this can grow fast. So this set of models are called the complete subset. Okay, so if k is small, we can, for instance, estimate all possible subsets. That's the complete subset. So we estimate all the regressions with 3 out of 10, with 2 out of 10, with 1 out of 10, with 4 out of 10, and so on and so forth. We run these regressions, we compute the predictions, and what we do in the end of the day, we average. We average them. With the aim of, with this averaging, we reduce the mean squared error. So in the back of our heads, the intuition is the same as bagging, like in terms of reducing the MSE, okay? The mean squared error. So we basically use equal weighted combinations of the forecast from all the subsets, okay, and that will be indexed by a small k. So we can choose small k from the covariance matrix of the potential regressors with when bk is small, okay, and we can do this recursively over time. Okay? This can be shown to be a sort of shrinkage, okay, but non-sparsity inducing. Okay, so we are not inducing sparsity, but we somehow are shrinking the coefficients. Okay? So basically, we are going to run the predictions that this is basically, this it's not really important for us at the moment, but we are going to compute these predictors. What's important is that we have this diagonal matrix that's a selection matrix, where we're going to take only the regressors that will enter each subset. So basically, there is a result that's if, okay, so here we are in the case where p is less than t, so OLS is well defined, okay? So in these situations, okay, we know as sample size increases, beta hat OLS will converge to beta naught. Beta naught is the true population parameter, okay? And we know that 1 over t x prime x will converge to sigma x, okay? And then for fixed k, the estimator of the complete subset regression that we are going to call beta hat small k bk, so that's the out of bk regressors we are selecting small k regressors, okay? This will be the OLS weighted by this matrix plus a term that's OP1, and these terms goes like this, okay? And in general, this is non-diagonal, okay? So it's not really OLS coefficient by coefficient shrinkage, but we can like have this relation between the complete subset parameters, estimators, and the OLS estimators, okay? If the covariates are orthonormal, so they are orthogonal, so no correlation, and the covariance 1 over t x prime x equals to identity, then the complete subset regression is doing shrinkage, because we have this term lambda that will be less than 1, okay, and which is multiplying OLS, okay? And subset regression will be numerically equal to ridge regression. Okay? And we can show that the subset regression will be given by this expression here, okay? That's just the sum of these diagonal matrix S. Okay? So we are shrinking the selection, the selected regressors, and in this case we can make the close connection to ridge. So the important thing is that it's not sparsity induction, but this nice property only when the covariates are orthonormal, which is not necessarily the case in most of the applications, especially in economics and finance. Okay? And this is just a picture that we can look at different values of bk, so the number of variables, as compared to the number of included predictors, lowercase k, that you have on the x-axis, and the shrinkage factor that you have on the y-axis. So you see, as the smaller is lambda, more shrinkage we are doing. The larger the lambda, then we converges to OLS, okay? Because remember, lambda is multiplying the OLS. So we can do a lot of shrinkage here if we take like lowercase k small. We are like including in each subset very small number of regressors. So we are doing a lot of shrinkage. If we increase k, so k small k in this setup, we again orthonormal, right? So K has close connection with the penalty parameter in penalized regression. Okay? And we can do the same thing, like looking at the expected loss or different, like what's the expected loss is the mean squared error. Okay, basically we are looking for here the loss, here K, and here how correlated is the regressors. Okay, so basically you see that there's a value of K where you really reduce the mean squared error. So that's to illustrate that. Again, so all these techniques like boosting, bagging, complete subset regression that we can put under this umbrella of ensemble, we are using averages. We are kind of combining models that individually they are not the best models, but when you combine them, you can have a very powerful model, okay? Where you can really reduce the mean squared error of your prediction. That's the idea of these ensemble techniques. Okay? So we can here, for instance, compare with OLS. So basically here we are looking at the ratio between OLS is in a simulated examples again, but the OLS with the complete subset regression. So if you are above 1, OLS dominates. If you are below 1, OLS is inferior, complete subset regression dominates. And we are looking at each plot is for a different value of big K. So here we have like MSE. Here we have lowercase k, okay? And rho is the correlation among predictors. So you see that in the vast majority of cases, complete subset regression reduces the mean squared error, okay? So it's better than just running simple regressions. And basically here's the same thing with reach. So that's the ratio between reach and complete subset regressions, okay? What we can see here is that there is regions, so dark red color shows areas where subset regressions it's better. So here, for instance, subset regressions better, subset regressions better, subset regressions better. So it's not really better when we have a very large number of small. This is all for bk equals to 8, and here we are looking at small k. Of course, if you have bk equals to 8 and you use lowercase k equal to 8, you're doing nothing. You're doing no shrinkage. So ridge is doing much better, right? But there's a region here of values of small k's where complete subset regression is doing much better than ridge. And there's some Monte Carlo in the paper where they compare complete subset regression here, ridge, elastic net here. The last block is elastic net. The pen is not working. Sorry about that. No, it's not working. Okay. So what's that? They are simulating models for different values of. They're showing the R-squares of the data for different values of signal to noise ratios and correlations among regressors. Okay. And basically, from the tables is that they show that in these simulations, okay, no sparsity and low dimension, complete subset regression is very competitive to other shrinkage methods. Okay, they do the same thing for lasso and bagging, showing that out of sample R squares for the complete subset regression is superior in this very controlled experiment. Okay. All right, so they have another applications where they look at return predictions. They basically want to predict the active premium, okay, and of the S&P 500, okay, and they are using like a bunch of predictors. So basically, what they show in the application is that there are a setup of covariates that dominates all the others. So in this plot, what they have is the active premium forecast for including all the 12 regressors. That's the red line, so you see that's really nervous. And they have including no regressions, just taking sample averages over the sample period. That's the yellow line, very smooth. Okay. They have the best k-variate complete subset regression, that's the red, the green, and the blue are all the other possibilities. And you see that the complete subset regression is in between a completely smooth function that's just the sample average and something that's really nervous, very erratic, that's including all the regressors to forecast the stock returns. Okay? And in these plots, they're kind of complicated plots, but basically what is shown in the plots is that if you take a look at the triangles, okay, and compare to the the red lines means that's the best the complete subset regression. These are kind of forecast variance, error variance. So we are reducing a lot the forecasting variance as you consider complete subset regressions. Okay, the blue circles are the variances testing for each covariate individually. Okay, the triangles, you take just the mean of all the forecasts, like the combination. The green line is just the average. Okay, and you can see that complete subset regression really can improve on the forecast. Okay, and the same thing with the R squares. There is a value of small k, the number of variables that you are combining, where you can improve the out of sample R squares. Okay? So in summary, it's a nice technique. Okay? No theoretical guarantees, no theoretical results like Lasso and family, but it's a very competitive technique in some cases. One question is how to implement this in really high dimensions, because all these illustrations in this paper is for a small dimension thing. So question for you is how to implement complete subset regression in really large dimensions. Okay, so thank you. See you on block 4.